Hello guys, welcome to the next section. Can you simplify that? Data reduction techniques. We will begin this section by performing cluster analysis using k-means clustering, and then do it using hierarchical clustering. And finally, we will be reducing the dimensionality with principal component analysis. Now we move on to the first video of this section, performing cluster analysis using k-means clustering. In this video, we are going to use the standard R package stats and cluster package to plot the results of our cluster analysis. We will be using the autompg.csv dataset here. So, before we read the data, let us install the cluster package. This is the code to install the package. The package has been installed successfully. After that, we will read our dataset. This is the code to do it. Next, we will define a convenience function to standardize the relevant variables and append the resulting variables to the original data. This block of code is the convenience function. Although the scale function does this, the names it assigns to the standardized variables mimic the original ones and hence can cause confusion. This convenience function creates more meaningful names by appending _z to the original variable names. So let's run it. We will now use the convenience function to standardize the variables of interest. For doing this, we will run this line of code. From the output, you can see that it has scaled 6 variables. We will now see the variables in auto. This is the code to do it. When we run this code, we get this output. We will ignore the variables number, model_year, and car_name. Let's now perform k-means clustering for a given value of k. So let's now set the seed using this code. We will now invoke the k-means function using this line of code. While invoking the k-means function, we have the option of selecting the specific k-means clustering algorithm by passing a value for the algorithm argument. If we leave this out, the function uses the Hartigan-Wong algorithm by default. Other options are Lloyd, Forgy, and McKee. Here, we are using k as 5. So, let's run this code. We will now examine the fit object that produces a lot of output. When we run the fit function, you will get this output. Due to the random choice of k starting points, your results may differ. From the output, we can see that the resulting model contains information about the centers of the clusters, information about which cluster each case of the data falls under, the sum of squares within each cluster, and finally, the proportion of total variability that the k clusters retain. We see that the 5-cluster solution retains 81% of the variability. This output also shows the components of the fitted model from which we can extract relevant information. We can summarize the information as: the clustering vector specifies the cluster to which each case belongs. The centers denote the center of each cluster. TOTS is the total sum of squares of the variables used. We have used standardized values, and hence this number represents the total sum of squares of these standardized values. Next is withins, and it is withins sum of squares for each cluster. Next one is tot.withins, and it is the total of the withins values. Between S is the total sum of squares if we represent each case by just the center of its cluster. The size is the number of cases in each cluster. Iter denotes the number of iterations used, and the final one is iFault, and it is an indicator of possible algorithm problem for experts. We have performed cluster analysis on 6 dimensions and thus cannot visualize the complete analysis. However, we can creatively use a pairwise plot to get an idea of the clustering and visualize the results. To get the pairwise plot, we will use this code. When we run this, a scatterplot matrix is generated. Here the points are colored based on the clustering vector from the results of k-means clustering. We will now load the library cluster using library command. The clustplot function from the cluster package can help us visualize the clustering based on the first 2 principal components by generating a bivariate cluster plot. This is the code for clustplot function. When we run this code, we get this clustplot. From the bottom of the plot, we see that the first two principal components explain nearly 92% of the overall variability, and hence the plot can be treated as a good representation of the overall clustering along the 6 original dimensions. Once the value of k is known, k-means clustering can be performed. We now show you how to ease the process of choosing a suitable value of k. Using what we covered, you can try out various values of k and choose a suitable one. To avoid the repetitive tasks involved in doing this, we suggest you use this convenience function. This method generates a plot and helps you to identify the place where the gain in performance tapers off, the elbow in the graph. It is sometimes referred to as the elbow technique. This function generates and plots the total withins across all clusters for values of k between 1 and 15, as you can see here. We can also supply an upper limit for k through the num_clust argument. Let's run this. Armed with the function, we can standardize the variables of interest, then run it. From the resulting plot, we can identify the value of k where the drop in the total withins tapers off, the elbow in the graph. We may choose k equals 4 or k equals 5 in this situation. If we really wanted very few clusters, k equals 3 may also be a good choice. We can always get a very low value for withins by increasing the number of clusters. However, we want to strike a balance between the value of withins and the number of clusters. That brings us to the end of this video. Here we performed cluster analysis using k-means clustering.